The next speaker is from GrAI Matter Lab. The speaker will be Jonathan Tapson. He's the Chief Scientific Officer for GrAI Matter. And I see, Jonathan, that you're online. Jonathan has spent part of his career doing sensor and instrumentation research. He's been able to spin out companies from his past research, and his new company is GrAI Matter Labs. So I'll turn it over to you now, Jonathan.
Thank you very much. Can you hear me okay?
I hear you fine.
Good. Thank you very much, and good morning, everybody, and good afternoon to those of you who are perhaps in different time zones. My name is Jonathan Tapson, and I'm the Chief Science Officer of GrAI Matter Labs. Yeah, and I'd like just to start by thanking Linley and his team for putting on the first ever virtual Spring Processor Conference and showing the imagination to go ahead with this when so many events have been cancelled. Okay, so what I'm going to talk to you about today is our new architecture from GrAI Matter Labs. And so we start with the question, why waste 95% of power at the edge? We consider that 95% of the power which is being used by most edge processors is wasted, and I'm going to spend a little time talking about that and then explain how we have an architecture that has improved that situation. First, to tell you a little bit about GrAI Matter Labs. We're a multinational company, but a small team, approximately 40 at the moment. Our headquarters are in San Jose, and that's where our product marketing and customer people are. Our technical work happens in Europe at 2 sites in Paris and in Eindhoven, where we basically do the systems and silicon and software engineering. The first thing I want to discuss, or to convince you of, if you like, is that the edge workloads are different to data center workloads. And we see a lot of processors being built for data center workloads. And our argument is they're different problems and they need different architectural solutions. The first thing on the edge is that everything on the edge happens in real time. So you have devices that need rapid processing of input and rapid response to that input. Even human devices like cognitive assistants, we want to talk to them and we want to get a response on the same time scale that we would get from a real human being. And I think we've all experienced frustration with the lags and things like autocorrect, or things as simple as autocorrect, but also with voice assistance and gesture assistance. And that's perhaps the slowest edge workload. If you go to self-driving cars or autonomous drones, you start to want control at rates much higher than human processors. And the extreme case of this is industrial robotics, where people may not be aware of this, but in industrial robotics, there's not yet a lot of adoption of machine learning techniques, simply because most of those techniques are happening on timescales where there isn't, the latency of machine learning inference is too slow. So there's a real need for this rapid response to new data sets. The second thing I want to convince you of is that at the edge, input data streams are continuous rather than discontinuous. And so by contrast with Facebook, whose inference has to deal with a picture of a cat and then a picture of a sunset and then a picture of a person, at the edge, we have continuous streams of video, for example, or continuous streams of audio. The forward-facing camera on a car doesn't suddenly cut away to some other scenery. It's continuously monitoring the same scenery. Industrial sensor ensembles are the same. They may be proximity sensors or LiDAR or radar, but they're continuously monitoring the same domain. And we see the same again with biosignals such as EEG and EKG, where we may be trying to infer the health of a human being in real time. A second key feature of edge data streams is generally the data rate is much higher than the actual information rate. And the reason for this is that real world activity is kind of sporadic. So you can have a cognitive assistant with, they typically have at least 2 and sometimes up to 6 microphones. They're sampling at 16 kilosamples per second and 16-bit resolution, so it's a minimum ½ megabit per second data stream. But they're listening for human voice, and the human voice is typically giving information at about 39 bits per second. And that's more or less independent of language or demographic. It seems to be almost a constant. So there's about a 10,000 to 1, maybe 20,000 to 1 dimensionality reduction between the data and the information when someone is speaking. And obviously most of the time cognitive assistants are listening to silence. An even more extreme case might be a smart doorbell, where most of them are now always on UXGA. So they're doing 59 megabytes per second sampling, but the actual information there is by and large, it averages out pretty close to 0 because there's usually nobody in front of your door. And even when there is, the true functional information, which might be the person's identity, is a very small amount of information. So there's once again, a very large dimensionality reduction, a lot of redundancy in the input. And here's an example of a speech waveform. Someone saying, "Eat your raisins outdoors on the porch steps," which is something probably a lot of us are saying to our kids right now. You can see even in the middle of speech, there are significant periods when there's silence and there's absolutely no need to process anything. Here's an example from video. This is a doorbell camera. And when you look at the scene, this is a cluttered scene. There's houses, cars, trees, mountains. But when you look at the difference between this and the successive frame, there's almost no update in information. The only thing that updates is the person on a bicycle riding past. And I want you to note two things about this. The obvious one being the amount of information changing in the scene is practically 0. But the second thing is that the changes are very localized. And in fact, in processing this kind of video, if you see a pixel change all by itself, you can almost be certain that that's noise because in real world signals, the changes are highly localized in space. So we set out to build an architecture that exploited sparsity, and there are multiple kinds of sparsity, of which I mentioned only 4 here. There's sparsity in space, which basically says that as our dimensions in which we're sampling get larger, the actual information or data points get, real data points get more and more sparse, and that's simply a property of information theory. There's sparsity in time, which I referred to. Real world changes quite slowly. Within networks, there's sparsity in connectivity, in the sense that even in a well-regularized neural network, there are a lot of 0 or close to 0 connections. And finally, when that network is operating, there's sparsity in activation. And Anil referred to this. He made reference to the non-processing of zeros, but in fact, it's not just about not processing zeros. If a signal is not 0, but it doesn't change, then there's quite often no reason to propagate that activation. So there are many companies now focusing on not processing 0 entries, but not processing unchanging activations was one of our goals. So we asked the question, okay, moving away from a standard DNN where every pixel and every neuron and every weight gets computed, can you process only the data that changes? I want to say a little bit about whether this is pragmatic. If you take pixels changing in an input frame, for example, and you ask how do they fan out in a convolutional neural network, they do actually create some fan out. I mean, if you have a 3x3 convolutional kernel, then each input changed pixel gives you 9 times the number of feature layers of changed upstream pixels. But on the other hand, you also get fan in. So for example, a max pooling layer is a 4-to-1 fan in, and given that it's 4-to-1 with a maximum function, there's only one chance in 4 that a changed input pixel will cause a change in the output pixel. So there's significant sparsity in possible in layers like max pooling layers. I also pointed out to you that the changes tend to be localized in space. And one of the things this means, as shown in this picture, is that the downstream activations overlap. So you don't get complete explosion here either. You tend to have to update a lot of pixels, but they tend to be the same pixels for multiple different input points. So that locality is consistent through the network. So we have designed an architecture that exploits sparsity, and this little cartoon just gives you a sense of the difference between a standard DNN shown at the top, where every frame and every neuron gets updated every time, no matter what. And we contrast that with GML's new architecture, which basically says, if you have a large change, yes, process all the change, but thereafter process only the changing inputs, and process only the meaningful activations as they go through the network. And so in this way, we managed to exploit all these different kinds of sparsity. So we have developed this into an architecture, and this shows a typical example of the kind of sparsity achievable. This is processing this is self-driving video, so it's actually quite changeable. The camera's on a car and the car's moving around. What it shows, the vertical axis is mega operations per frame. It shows that if we process everything, we do 28 mega ops per frame. If we focus on sparsity, the light blue curve shows the real amount of processing required, and the dark blue curve shows the average, which is 1.7 mega ops per frame. And you can see that, in fact, the amount of operations required drops to basically 0 from time to time. If the car is standing still and nothing's happening, there's no processing required. So this is typical of the kind of sparsity that can be achieved. So we have built our first chip, and it's available today. It's called GrAI 1. It was built as an accelerator chip, and largely just as a proof of concept that this can work. And at the bottom, you see a picture of the layout. It's basically a 14 by 14 array of neural cores. The top shows a single core layout, and the light gray there is memory. So this is our intention is to hold the entire network in memory, and it's basically, it comes down to semantics. You could call this compute in memory or compute very near memory, but the memory is on the same chip and in the same region of the same chip as the compute infrastructure. So this chip has 196 neuron cores, which managed to instantiate 200,000 neurons. And we have tested it. It's working very well. It's programmable we have a full SDK, which I'll talk about in a moment. Yeah, let me tell you a little bit more about that architecture. So here's just a sense of what's actually on the chip. Each neuron core has a router, and therefore the neurons are all connected together by a fairly conventional network on chip. And I say fairly conventional. I want to make a point that this is not intrinsically a spiking neural network. It's an event-based neural network. So what are being passed around between these neuron cores are not spikes, but actual numbers, 8 or 16-bit numbers, so that the system can actually look at each packet coming in, each packet being passed around, and can think of it, it can process it as an event, as a number, or as a spike, if that's actually what the network wants to do. So yeah, being an accelerated chip, it's designed to have a host system, so it's got just very simple GPIOs and control interfaces. What actually happens in one of these neurons? This is a very simplistic picture, but basically events come in and they're processed on a FIFO basis. They're multiplied by locally stored weights, and the neuron states are stored locally and are updated. And then the compute which happens, and I'll say a little more about that in a moment, may not actually produce an output event. It may be that there's nothing to say, so to speak, in which case no event gets generated necessarily. But if an event does get generated, it goes out through is written back out onto the network to another source. I want to make the point also that these neurons are not simply spiking neurons or ReLU neurons or sigmoid neurons. They're effectively little ALUs. They have about 30 functions, and they can do basic math. They can add, they can multiply, they can do greater than, less than. You can think of them as a little RISC CPU with neuron functionality added to them. So it can also, this whole system can be processed as a straightforward data flow computation engine. And probably the most important information on this slide is point 5, which says neurons have state. It's impossible to compute differences or to compute sparsity unless you know what the last state of the system was. And the GPU type systems, which are focusing on massive matrix multiply and accumulate efficiencies, make a virtue out of discarding state and holding intermediate states only in registers in order to avoid memory fetch and execute. And that's where their efficiency is optimized. But if you're going to focus on sparsity, you have to keep state, and that's a core departure in our architecture. So we have a hardware development kit pictured on the right here, and we have a demonstration of it in a self-driving situation. I'm not going to demonstrate it in this talk, but we have a breakout room later on today, and I encourage you to come and see it. So what basically you see in the picture is that a street or road scene is shown on a monitor. A camera is used to video that street scene. So it's a real simulation, if you like, of a self-driving video. And the system computes the steering angle, which is required to keep the car on the road. Okay, Linley mentioned earlier that software is critically important in these new architectures, and we have a fully featured SDK, which you are welcome to contact us to get training in and to try out today. There's nothing, I think, completely surprising about it. We have TensorFlow as a high-level API interface, so you can generate models. And as with everybody else, we have not instantiated every single TensorFlow kernel, but we do have the ones which will cover 95% of current applications. It's also possible to program this accelerator directly in Python or C++, because as I mentioned, it's not just a neural network inference engine, and we in fact have used it as a DSP. So we've done FFTs on it. It's incredibly fast because it's extremely parallel. And we are currently teaching it how to do singular value decompositions, and you can use your imagination to think why that might be a useful output. So the high-level representation gets down, compiled into Python or C++ representation at the neuron level. And then the key feature of this compiler is the mapper, and which is basically the engine that takes the conceptual representation of the network and decides which neuron it should run on and how they should be connected. And obviously optimizing that is key to the functionality of this chip. And then that mapper output can get passed to a simulator, which we or you can use extensively to figure out whether the system is optimal. And having decided it's optimal, we can generate the chip code and then run that on the chip, and we have the usual suite of runtime support available there. As a demonstration of how this could be used, we've implemented NVIDIA's PilotNet network on GrAI 1. It is not a large chip, being just a proof of concept, but obviously we are scaling up in the future. But this is basically a network that takes a street image and computes a steering angle output for a car. And these are the kind of results. If you run this network raw in TensorFlow, you're looking at about 5 mega operations per frame, per second. If you run it on the GrAI 1 chip, we're managing, the sparsity cuts it right down. So we only have to do less than a mega operation per inference, about 0.67 per inference. And because of the enormous parallelism of this architecture, we can do that at 3,600 frames per second, which is completely ridiculous for this particular use case. But it gives you a sense of why this could be a very useful edge architecture in creating applications. I think one of the core messages out of Linley's introduction this morning was that each architecture is going to find its sweet spot in application space, and we are very comfortable that with these kind of inference rates, this architecture is going to show itself very well. So in conclusion, what have I presented for you today? We have a new architecture that gives us very low power and very low latency on real-time sensor data. So we think of it as giving live AI. Anytime you've got AI, that has to happen in a feedback loop very quickly without necessarily waiting for large batch processing. This is a good architecture. We have the architecture is called Neuron Flow. It's optimized to exploit sparsity. And we currently have both our GrAI 1 chip, which is available, and we are working with several partners to have them use our HDK in their applications. If you believe this may be the right chip for your application, please get in touch. And finally, we have a software development kit, which is basically available to anyone who is interested to take a look at that. And I encourage you to get in touch if you're interested. And that's it. Thank you very much, everybody.
Thank you, Jonathan. And you can go ahead and turn off your screen sharing, and we'll move into the Q&A. Okay, so question on the event-driven or looking for pixels that change from one frame to the next, do you store the entire input frame coming in from a camera, and then buffer that to look at the changes?
You can think of it as doing that conceptually. We have a couple of tricks which allow us to avoid storing the whole input frame, and they're currently the subject of patents which are in progress. So I'm not gonna go into any detail on that, but just to say, it isn't necessarily necessary to store entire input frames.
Okay, so there's some secret sauce there. So if you are looking at pixels that change, can this be used for object tracking?
Yeah, it's a very good technology for object tracking, and you may be familiar with the dynamic vision sensors, which are basically event-based cameras which respond only to change. And so the combination of a GrAI chip and an event-based camera turns out to be a really superior object tracking.
Oh, I was going to ask you that. I should have assumed that you were already familiar with somebody like Prophecies building these event-based cameras.
Yeah.
Is there an advantage to working with that versus a conventional imager?
So event-based cameras, without wanting to go into a big digression on event-based cameras, but they suffer because they're superbly good at detecting change and detecting motion and inferring stuff from that. But most of the data sets which are available at the moment are classification data sets. Who's in the picture, what's in the picture, these very static problems. And so they tend to benchmark badly because people are using them for the wrong problem. As soon as you start benchmarking them on motion situations, dynamic situations, I mean, it is a dynamic vision sensor, then you find that they actually significantly outperform real cameras. And as I say, we think it's a very nice match to our chip, but the fact is, we're not in the position of selling dynamic vision sensors. If Prophecy and Samsung succeed with those, that'll be very good for us. But we're focused on regular video because that's where 99.49% of the market is at the moment.
So the potential performance you talked about, 3,600 frames per second, that's impressive, but there's a real frame rate coming in that's much less than that. What resolution and frame rate can you support?
So this is a very small chip at the moment, and it was in fact never designed to support video loads. It was designed to support biosignals and other bespoke, if I can put it that way, sensor suites. But it's nice that we can support video, but we haven't really tried it on anything larger than QVGA. We are currently obviously designing a chip that is going to have, if you like, one of its core applications areas will be video processing, and that'll obviously be able to take in large video frames.
Okay. So yeah, I learned something new listening to your talk. It seemed like with the other functions you can perform, can you do some sensor processing? I thought when NVIDIA developed the PilotNet that they were actually fusing some of the vehicle sensors with images. Can you do some processing on your chip?
We could do that, and we're working on a couple such applications at the moment. But in that particular PilotNet example that I showed, we're just doing the video processing change there. There's absolutely nothing stopping us from taking in an extra sensor and adding it in if the network can perform the inference.
Few people are asking about how much memory total is on the chip.
Sure, that's kind of a gotcha question because, and the short answer to it is of the order of 7 megabytes or so, but it's a gotcha because that doesn't translate into the weight space. And if I give you an example of what I mean by that, if you consider convolutional neural networks, they generally are reusing a very small number of unique weights multiple times. And so I implore, if I can use that word, anyone translating that amount of memory into a parameter space to remember that that's the number of unique weights which might be stored on this chip, not the number of individual weights in a given network. So the number of connections in the network is a significant multiple of the memory size.
Okay.
And again, that is subject to a couple of patents, but I mean, I think anybody can work out the general drift of that answer.
Or they can try and look at your patent application.
Yeah.
Right. One of the interesting questions we have is, can the user change the sensitivity for the detection? I mean, is that?
Yeah. In fact, that's a big part of the optimizing process. Is you can trade off accuracy and sensitivity for power. And I think we're starting to see this, and I think a lot of people are starting to talk about these applications where, take a smart doorbell, for example, you might want to have extremely low power as somebody gets into the scene, and then only fire up high sensitivity, high power to do face recognition, and then turn it off again at the moment you've done that. And sure, we're capable of those kind of thresholding operations.
You could adjust it dynamically with software.
So not with software, but the network would itself have to adjust dynamically. Yeah.
It would be something you would do during the training.
Yeah, it would be something we would do during the optimization. So I guess during the training.
Yeah. Okay. One of the other questions from our audience is, do you have a simulation environment that somebody could use to learn their way around the SDK without having to have the chip?
Yeah, certainly. In fact, we're offering that kind of training on quite a regular basis at the moment. So we haven't at this stage just made it open on the web, so to speak, but we have been very undiscriminating, and if people get in touch, we set them up for an hour or two training session with one of our, which can be done online, with one of our field application engineers and get them going on that.
It's an interesting question. Let's see. Wanted to know if a jitter in the processing flow would affect this detection of changes, a jitter from looking at the network connections or any of the other, I think, I/O connections. Would that affect the performance?
So we've put a great deal of effort into trying to deal with data flow through the situation, and I think those in the audience who have some knowledge of data flow processing, they know that controlling the synchronization of data through a data flow processor is not a simple thing, and we consider that we've got that situation solved, and it's not out of the question that some future application might cause trouble, but it isn't causing trouble at the moment. If that's the jitter we're talking to, if the person is referring to, I don't think the person was referring to camera jitter, just reading the question myself.
Yeah, right. Okay. One of the questions I had, do you have any measurements of the accuracy?
So in the self-driving car example, the accuracy is in terms of steering accuracy, the position of the steering wheel that is output by the neural network. And we have taken care when working on Sparsity to keep that down below 2 degrees RMS error as a kind of measure, because we figure if you think about a driving environment, I mean, I'm not sure many people could actually physically detect a 2-degree out of 360 difference on their steering wheel. It's pretty much negligible. So as you yourself said earlier, it's an optimization that the user performs to say, I'm going to trade power for accuracy. And we just arbitrarily set a threshold of 2% as being sufficiently accurate for our test figures.
Okay. And would this technique work for things besides object recognition?
Yeah, certainly. In fact, I think tracking is going to prove to be one of the really useful things. So again, these dynamic situations. If I may say again, bringing it back to the driving situation, when you drive, you don't set an absolute steering angle as a human being. You don't set an absolute steering angle to go down the street and then go. You're continuously correcting it as your car motion feeds back to you what you should be doing. So the absolute error per steering angle is not a critical thing, but and what is much more interesting is how fast can I feed back that I'm going in the wrong direction and converge on the correct decision. So those of you familiar with control theory will know about things like bang control, which basically says you can control quite adequately with full scale slew of the input signal to your system, provided the timing is right. And so you can trade off accuracy of the input for precise timing of the input. And this is a very good way of doing feedback control. And okay. I think that we'll see our chip getting a lot of use in those kind of situations.
Thanks, Jonathan. That was a great talk. We'll see you in the breakout session later on today.
Thank you very much. Thank you, everybody.